Welcome back everyone to another video of Mathverse. So today's class we are going to discuss about rational numbers. As we had discussed last video, rational numbers are, and all of you are also aware about it, the rational numbers are numbers in the form p by q, where p and q are both integers and q should never be equal to 0. So today's class, let's continue with the revision on rational numbers. We will be discussing about the properties of rational numbers and then we move on to solving few problems. So let's start with it. The first property is closure property, which means that when I add two rational numbers, the sum is another rational number. When we subtract two rational numbers, the difference is also a rational number. When we multiply two rational numbers, the product is also a rational number. And when we divide one rational number with another non-zero rational number, then the quotient we get is also a rational number. So closure property is applicable for rational numbers in whatever type of operation you do. The second one is law of commutative. Law of addition and subtraction, which is applicable for rational numbers. Right? So which means that if I have a of commutative property of addition, a plus b plus c by a. This is one rational number, this is another rational number, which is also equal to this plus this. Right? So it is not applicable for subtraction or division, but it is applicable for commutative law, is applicable for addition and multiplication. Then the last one is distributive law. So distributive law of multiplication in terms of addition and subtraction. So if a by b is one rational number, I multiply it with this, so I get a by b into c by d plus a by b into e by f. We have done multiple applications of these laws or properties of rational numbers. So this is distributive law of multiplication in terms of addition. If you change the sign to subtraction, even then the distributive law holds good. Right? So these are the three major properties. Then we know about multiplicative inverse, which is nothing but reciprocal of a given rational number. Okay? So let's start doing few sums. So addition of multiplication, addition, subtraction, division, we have done lots in 7th and 8th grade. We are not going to repeat that in 8th grade. We take only one subtopic, which is, as I have discussed in the last class, that there are infinite rational numbers lying between two given rational numbers. So let's try finding few rational numbers. Suppose we get a sum which says that you have to find 5 rational numbers lying between 3 and 4. So 5 rational numbers lying between 3 and 4. Right? So see, the easiest thing is, can you think about decimal numbers which are lying between 3 and 4? Yes, we can. 3.1, 3.2, 3.3, 3.4, 3.5. Actually, there are many. 3.12, 3.11, 3.13. Right? There are many. So we have taken only 5 of them. 1, 2, 3, 4, 5. Now, can I convert these decimal numbers into fractions or rational numbers? Yes, we can. So this becomes 31 by 10, 32 by 10, 33 by 10, 34 by 10, 35 by 2. So decimal numbers can also be written in the form of rational numbers, right? So decimal numbers are also rational numbers. So this is the easiest way of finding. There are many. If they tell you 10 rational numbers, 20 rational numbers, you can find between two given natural numbers or rational numbers, right? So this was an easy sum. I hope it's clear to everyone. Now, instead of 3 and 4, let's try to find rational numbers between the rational numbers 3 by 5 and 4 by 5. Okay? Now let's try doing this. So here, what we can do is we can make them as, we can increase the value, right? We can find an equivalent. So here, the first thing is, this is an easy problem because they are like fractions. The denominators are equal. So what we can do is, we can do the same thing like we did in the previous case. We can write 3.1 by 5, 3.2 by 5, and so on. Right? 5 rational numbers. 3.1 by 5, you can write it as a rational number as 31 by 50, 32 by 50. We can do that. Or the other way of doing it is, you increase the value of the numerators. How do you increase the value of the numerator? 3 by 5, I can write it, multiply both numerator and denominator by 30 by 50. So 4 by 5 becomes 40 by 50. And now we can change the numerators, 31 by 50, 32 by 50. We can find 10 rational numbers between these two. Right? Very simple, very easy. Either ways are good. So whichever way is comfortable for you, whichever method is comfortable for you, you can go ahead with it. I hope I have been able to put across and make you understand the concept, the basic concept behind it. So now let's move on to the next concept. Now, as we have discussed in the previous problem, all decimal numbers can be written as rational numbers. So, decimal numbers are different types. You have done it in 7th grade. Let's just quickly recap them. Terminating decimal numbers. So, decimal numbers which come to an end. For example, 1 by 5. 1 by 5 can be written as 0.2. So it has just one decimal number after the point. 1 by 8 can be written as 0.125. So these come to an end. These decimal numbers come to an end. So they are called terminating decimal numbers. Now for example, think about 1 by 3. 1 by 3, when I convert it into a decimal, it is 0.333 and it goes on, right? It is a non-terminating, like which doesn't come to an end. If for example, we take a number 3 by 7, okay? 3 by 7, let us start. Try to convert it into decimal. 7, it goes, doesn't go, so put the decimal point. 4 times it goes in 30, 28. 2 and 0, it goes 2 times. 14. 6 and 0, it goes 8 times. 56. 4 and 0, it goes 5 times. 35. Then again 5 and 0, it goes 7 times. 49. So see, it goes on continuously. So this is also a non-terminating decimal number. Now this non-terminating decimal number has another part which we did over here just now, 0.3333. So there are few rational numbers which when converted into decimals, the digit after the decimal point keeps on repeating itself. So those types of numbers are called non-terminating recurring decimals. So recurring decimals are also of two types. One is pure. Pure means the digit, or it can be a single digit, it can be a double digit. The digits repeat themselves. There are only repeating digits after the decimal point. Mixed consists of different digits, few which doesn't repeat themselves, and then digits which are repeating themselves. So we can say, you can think about pure is, the example of pure is 1/3. Think about an example for mixed, repeating, recurring, non-terminating decimal. So 11/30 is an example of mixed recurring decimal. So if you divide 11/30, see it doesn't go, so put a decimal point at how many times does it go? 3s are 90. So this is 2, 0. How many times does it go? 6 times, 180. Again 20 and 0, 6 times. So it has fallen into a loop. The 6 will go on repeating. So this is an example of mixed recurring non-terminating decimal. The 3 is a digit which doesn't repeat itself. 6 is repeating itself. Okay. So let us try to do few sums based on this concept. So let's try to solve these three sums. Now what do we have to do? Just looking at the decimal and the rational number, we have to find out whether it's a terminating decimal or a non-terminating decimal. Now how do we do that? By looking at the denominator. The denominator over here, what are the factors of 35? 5 and 7. So whenever the denominator has the factors in terms of 2 and 5, only factors in terms of 2 and 5, they are all terminating decimals. So rational numbers whose denominator has factors in terms only in 2 and 5 as factors, then they are terminating decimals. But if they have a factor, any prime number as a factor apart from 2 and 5, they are non-terminating decimal. So here 35 has a factor 7, which is a prime number, so it is a non-terminating decimal. And the second one, 16. 16 can be written as 2 to the power, 2 to the power. So 2 into 2 is 4, 4 into 2 is 8, 8 into 2 is 16, 2 to the power 4. So the factors, it can be written only in terms of 2. If I break it down, only in the prime factors are 2. So So let's start doing these three sums. Now what do we have to do? We have to determine that whether the given rational numbers are terminating or non-terminating decimals without actually dividing them and converting them into decimal numbers. So how do we do it? The denominator has to, we have to check whether the denominator has the prime factors. What are the prime factors of the denominator? If it is only 2 and 5 as the prime factors, then they are terminating decimals. If they have a prime factor apart from 2 and 5, then they become non-terminating decimals. So 35, what are the prime factors of 35? Converted as 5 into 7. So 7 is a prime number apart from 5, so it's a non-terminating decimal. Here it is 16. 16 can be written as 2 to the power 4. So 2 is the only prime factor of 16. So this is a terminating decimal. 14 can be written as 2 into 7. So again 7 is a prime number which is a factor of 14 apart from 2. So this is a non-terminating decimal. I hope this concept is clear to all of you. If you have any doubt, you can put it in the comments and I will try solving it in another video. Thank you. So next class we will start with irrational numbers.